discussed last week. Hip. Yeah, hip. That's the one part. What was the reason that we started discussing on hip? Priority queue. Why we're starting from an idea for priority queue, and then we take a look at the different methods to implement that priority queue. It was the one, and in order to understand the hip, the things that we need to know beforehand was a tree, special type of trees up there. So, three properties of the hip has to be binary tree, complete tree, stuff like that. And you're gonna throw another property on top of it, either going to be a max or a mean. So, if it's a max, what's on the top should be bigger than what's on the below. If it's a min, it's opposite way. So what was the definition? It's a binary, complete binary tree with a max complete binary tree. Is it something like that? 맞죠? And then we did take a look at the because we can number each node, and we can use those numbers as an index into the array, so we can easily store those tree structure into an array format. Right? That was discussed. And then we all know that trees are much more flexible if we use a linked list. Right? Like the example that I showed you last class or the class before that, and then you have to add a couple of pointers in it, and it would be much better in terms of time complexity if your trees have a special, if your trees are in special circumstances, like it's on the left side have one. Skewed trees that we discussed, there will be a lot of gap between the elements. Hip sort. Hip can be used to sort an element. What was one part only? What was the main thing to remember using a hip sort to a conventional sorting method that we know of in terms of time complexity? What was better than the other sorting algorithms? In worst case, of course. What was the time complexity to insert and delete an element in a hip? Log n, right? If it's a hip, then just going around each height, right? Height of a tree, if you have an n node in your tree, is log of n, right? So it's usually insert and deletion is log n. What was the time complexity? Worst time complexity for making a hip? And I mean, there was some formal formal definition of why we use why it is an order of n. Just simply because each height that we take a look at the every elements in each height, you do that for every levels. So simply put, you have to go through the every elements in the list. That's why in worst case order n. So what did I did after that point? Every time if I take out an element from the top in a hip, then I have to make it hip again. I have to find a replacement for the empty spot. No? No? Yes. And then you take the elements every single time until there is no element left. Each operation would take a log of n. 아니야? 힘들어. log of n. and log n. You know? But conventional sorting algorithm that we know they usually achieve the worst time complexity of n squared. So this time, the first time we've introduced the n log n sorting algorithm. It's a slightly better time complexity sorting algorithm. So that was the main part in terms of time complexity, right? And yeah, hip sort, yes, no. So n log n, hip sort, n log n, and log n, and log n, and log n. And they're slightly better than n square algorithms. So we kind of understand why we consider hip sort as n log n. So put the so algorithm was like this. Put the elements to be in the sorted and put a priority queue, initialize the heap, so you're making a heap 3 ways. Extract, delete the element from the priority queue. Priority queue, one at the top will be the one that, which way you want to do it, it's up to you, but that depends on if you use a min tree or max tree, it will be ascending or descending order you can do. The main priority queue is used, elements are extracted in a non-decreasing order of priority if max priority, vice versa. And then, okay. So, in terms of applications, HIP, sorting, machine code scheduling, Huffman Code. Okay, this was a figure just briefly explain how to use a max priority queue, HIP, to sort in elements. We have take a look at this last class. Anyone start to take a look at the code on your textbook? Some of the sample code on implementing, or there was at least few code on the inserting an element and deleting an element. You do take a look. Okay, I will probably go over that probably last week of the class. In terms of coding and stuff. And then what I just explained, why we consider this operation as an n log n time complexity algorithms. You have to do a reinitialization every single time you extract the elements, right? Compared to the order of n square sorting algorithms, hopefully it will be better, right? So the review that we did. So and then we moved into the machine scheduling problem. This is also applications of a HIP. We didn't take a look at the one suggested solution. We just discussed what's the problem. M identical machine. There's M machines. There's n tasks, n jobs to do. How you're gonna distribute each job to which machine will have an impact on when you can finish the entire job. So how can you schedule each job to which machine? That was a problem. We start discussing this problem, and then what was the conclusion of this problem? How do we classify this problem as what? How do we classify this problem? There was a term to describe this type of problem that doesn't have a exact solution in it. MP, right? MP hard problems. Okay. The definition is given, but I explained it like there is no formula, no reasonable formula to solve this situation. I mean, for human beings, we can do this in head and probably find the best possible one that we can think of. But in theory, there is no one formula that gives a one and only answer every single time. And I also discussed a similar problem like this in real life as what was the example that I gave you? When they try to schedule the delivery every single morning, they have to consider distances they have to travel. When they stack their product on their trucks, the longer, the ones will be delivered at night, it will be at the back of the truck. The sooner that you think that you will deliver will be in front of the truck so they can take it out easily, so they can save time. So everything is about to minimize the service time. This one as well. So you might be able to use this HIP as a mechanism to minimize the service time of all these jobs. So minimization problems. Machine scheduling problem is to assign jobs to a machine so that time at which the last job completes is a minimum. I have 5 jobs if I can finish in some time, but hopefully fast enough. So example they gave was 3 machines, 7 jobs. Job time is 6, 2, 3, 4, 5. Every job has a different time requirement. And then I remember last class someone come up with a better way of scheduling these jobs. That's also okay too. But some possible scheduling, and they give certain things. I think they looked at it as one of the optimized one. So they schedule their problems so every job will be finishing at 21 seconds. There could be others. Some solutions may be longer than that. Some solution, if possible, might be smaller than that. So in this example, what is the finish time of the schedule? It was 21 seconds. Objective is find the schedule with the minimum finish time. So minimum finish time with scheduling is NP-hard. Discuss this as a review. I'm just doing this because some of the terminologies is not very familiar to us. Anyone look it up on this NP-hard problems on the wiki, for example? wiki 같은 데 봤어요 혹시? I think I suggest you look it up on the internet. Type in NP. You might run into other type of definitions like NP complete, NP hard. They have a list of problems that has NP hard. You will run into very similar definitions on those web pages as well. Class of problems for which no one has developed a polynomial time algorithms. Polynomial time algorithm. Polynomial again as 뭐였지? 다차 방정식, 다항 방정식. 다항 보고 다차는 뭐냐? 항이 여러 개 있는 거고 다차는 차수가 높은 거가? 그게 그 얘기 아닌가? 아닌가? 아니야? 그래요? 미안합니다. Polynomial time. No algorithm whose complexity of order n to the k, m to the l is known for any NP-hard problem. So known for any constant k and l. It simply means it's very difficult to find. No, not very difficult. It will be impossible to find any algorithm that has a reasonable time complexity. If I'm able to find any algorithm that does this scheduling in terms of n to the 10, n의 10승. Even if I can find n to the 10, is it useful? Probably not. It simply said it's even impossible to find those high complexity ones. n의 10승 되는 것도 못 찾는 그런 알고리즘이라고 보는 거예요. n의 10승을 찾아도 써먹을 수가 없겠지. 되게 느려서. 그죠? 그런 알고리즘조차 찾기 힘든 문제라고 보시면 됩니다. NP stands for non-deterministic polynomial problems. And P-hard problems often solved by heuristics. So it's an approximation algorithms, heuristics. Let's do our best. Let's see what our brain can do. Let's come up with some ways to do this. Some ways to do this. As simply as it gets, like you take out the shortest time first and put it into every single machine. That is a one heuristic algorithm, right? Or you do an exact opposite. You take out the longest job first and put it in the queue. That's also okay too. Of course, it will have some impact on the final finish time, but those are the solutions. 제일 긴 거 먼저 찾아서 긴 거 순서대로 머신에 넣어도 그것도 알고리즘이잖아, 그죠? 물론 시간이 오래 걸릴 수도 있고 더 적게 걸릴 수도 있고 하지만 하나의 솔루션 중에 하나죠. So you can call that as a heuristics. There could be many other approaches like that. If I do a random, I just pick any jobs. Doesn't know how long each job it takes. Still a heuristics. Still a heuristics. Approximation algorithm is 괜찮지? It's close to maybe the best possible solutions. So it's a similar idea, which do not guarantee the optimal solution. These heuristics or approximation algorithm will not guarantee the best possible solution. Like we looked at it, there is no way to find out the best possible solution. algorithm, there is no algorithm that provides the best possible solution. 그러니까 some heuristic algorithms will provide the solutions. Heuristic algorithms will provide a solution that might be close to the best one possible. So you will hear this heuristic, the term heuristic, everywhere. Most likely, many algorithms that you try to implement, other than those simple sorting or quite obvious algorithms, many real-world problems. If you're looking for the algorithm, there is no one algorithm can do the job. So you will have to experience many different options, many different heuristic algorithms, and you might want to find one that fits your need. 휴리스틱이라는 단어를 상당히 많이 듣게 될 거예요, 앞으로. 그래서 이렇게 휴리스틱이라는 단어를 들으면 이렇게 생각하면 돼요. 그냥 나는 어떻게 이해하면 되냐면, 이거 되게 어려운 문제라 어떤 알고리즘 하나가 있어서 딱 맨날 좋은 답을 줄 수 있는 알고리즘이 없구나. 그러니까 여러 알고리즘 중에 그나마 비슷해 보이는 놈들 중에 하나를 고르면 되겠구나. 그냥 그렇게 이해해요. 비슷한 놈들 중에 하나가 다 휴리스틱 알고리즘. 이렇게 표현하는데 상당히 많은 문제들에서 휴리스틱이라는 표현을 쓰게 될 겁니다. NP-하드라고 부르진 않고 대부분 휴리스틱, 이 문제에 대한 휴리스틱 알고리즘은 뭐 요거 중에 하나 뭐 입맛에 맞는 거 쓰세요 할 수도 있고 데이터셋에 따라서도 바뀔 수도 있잖아요, 그죠? It also depends on how you organize the job length. Some heuristic algorithm work most of the time, but if you run into very weird situations, that job distribution is quite weird. Every short job, and then there's the longest job. Then your previous heuristic algorithm may not fit the best. So you might want to use a different heuristic algorithms if you wish. So one of them is, in most cases, they suggest something like longest processing time, LPT. LPT rule is a good heuristic for minimum finish time scheduling. Of course, in most cases. What is it? Longest time. So, name speaks itself. Longest one first. Longest processing time first. Job is scheduled in a descending order. We can do this by using what? Pip sort. Pip. We can do this sorting from the scramble array to this one. So if I sort them out, 10, 14, 7, blah, 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 and then each job is scheduled on the machine on which it finished the list. So I have 3 machines here. I put 14 on machine A, and then I'd like to find out which one I should put it in. Next job is 10-second one, but A still has a 14. I cannot give it to it, so I give it to 10. B, I'm sorry. 10B. Not good today. And then for the next job, which takes is 7, when I'm selecting this, you keep making head and removing a node from the top, right? Think of that. And then you choose 7, with A and B is not finished yet. No, A and B is not finished yet, so I have to go to C, 7. And then I wait, we'll go another 7 seconds. But A and B, A has a 14, B has a 10. So after 7 seconds, C is the only one who is left for another job. So because A and B is still running. 7번 주고 7초 지난 이후에도 아직도 10이랑 14는 3 남았고 7 남았으니까 C is another idle one, just not working one. You put 6, 13. So after 13 seconds, at that moment, B probably finished. B was given a job of 10. And then it goes, the next job is available for 5 seconds. After 6 is 5. I give 5. Likewise, you given a job to the ones those finish the list. In what order? You give the longest one first by doing a sort. So LPT, one of the heuristics, and obviously this gives a better finish time from the previous example. The previous example gave you 21 seconds. This one, if I finish all the job, was 16 seconds. Okay. So this is something that I wanted to, right? I wanted to minimize the service time, the time that finished entire jobs. So LPT usually works fine, but I'm sure you can find some special cases that LPT might not be the one to choose. 뭐 LPT가 안 맞는 경우도 있을 것 같아요. 물론 데이터셋이 어떻게 따르냐에 따라서 갑자기 짧은 것만 막 있다가 긴 게 나온다던가 아니면 고만고만한 애들끼리 모여있다거나 고만고만 5, 6, 5, 7 뭐 이렇게 하면 헷갈려서 LPT보다는 LPT 같이 하면 그냥 하나하나씩 줘도 되는 경우가 있을 수 있고 If you find a special cases, then find another heuristic that fits the best. It's completely okay because we don't know, we don't have the one and only algorithm for such situations. So hopefully this example gives you idea for NPR and LPT is introduced that we can use a hit as one of the heuristic approaches to solve this type of situations. So, brief ideas on NP and applications of the hit LPT. So they give you another example on doing this, but it's a piece of cake. I'm sure you can do this in yourself. You can take a look at also figure 12.10 for doing this. 이거 뭐 쉽지? 뭐 그냥 힙솔트 tree it's not. I'm not even asking to draw a 힙솔트 tree. Just do it. Sorting in your brain and just do the same thing and see how what is the finish time of doing this example. Do I ever ask such problem in the final exams? That's wrong, God. Probably not. I may ask you to do a procedure for adding an element or removing elements or even making a hip tree from scratch. But I'm probably not going to ask you this type of LPT ones. It's quite obvious. Quite obvious. LPT using a min hip. Min hip has a finish time also. Opposite approach. Min hip has a finish time of n machines. The initial finish time is all 0. To schedule the job, remove a machine with the minimum finish time from the hip, update the finish time of the standard machine, and put the machine back into the min hip. It's okay. This one I can ask you to skip one. It's okay. But what's important is the idea for NPR and one of the heuristic is LPT for typical problems. This one, just another variations. So it's okay. So you can skip this one. I will draw. Huffman Code. I'll probably give you another 2-page long slide. Not a slide. It says a quick tutorial on the Huffman Code. Okay, what's Huffman Code? Huffman Code. If I take a look at the slide, they say something like text compression. Text compression, frequencies, the keyword like text compression, reoccurrence of the substring, relative frequencies. That might be related to the reoccurrences of the substrings. Code is prefix of another blah blah blah. It's something like a tree with a frequency in it. Frequency is what? Simply put as how many times does it appear? I count A appear maybe 4 times in a sentence. So if you measure those frequencies and what symbols are there, maybe with that information I can construct a tree. Somewhat like here, maybe. How does it make a tree? So let me read it. For text compression, the LCW method relies on the reoccurrence of the substring in the text. Some compression algorithm will take a look at how many times the same string appears over and over again. Like the sentences that I'm speaking, maybe I speak I all the time. I. In one or two sentences, how many I's are repeating? So reoccurrence of the substring. So I count that. Huffman code is another compression technique, text compression method, which relies on the relative frequencies, number of occurrences of the symbol, ABC characters, with which different symbols appear in the text. Why do they say it's a compression? And they consider how many times does it appear. Compression is what? 압축. What is 압축? We briefly take a look at compression in Introduction to Computer Science in the last year. Not last year. This year. You guys came in this year. 너무 자주 봤더니 언제 왔는지 잊어버렸어요. So it's basically, it was like, if I remember those examples, I don't remember exactly those. Then I count how many times was it something like this? There is 2i, 4x, 2z, 2w, something like this. We can have it, maybe we can use this information to describe it later. Same idea. I just counted how many times they appear in the string. This is the information that I want to send. Maybe I can, in order, idea of compression, if I need to send this information, how many? 2, 3. Beginning, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each takes a 1 byte, for example. So in order to send this one out, I might need 10 bytes. But if I compress in some way, I may just send 4-byte information. Then I may be able to get back to this original string. That was the idea for this, right? Compression, when you do a compression in your programs, usually files get very smaller. That is the idea for a compression. I make it smaller, and according to some of the rules later, I can bring it back to the original documentation. So if you do a zip on the, for example, Excel files or Microsoft Word files, the file size gets really smaller, and then if you give that zip file to later, click it, unzip, they will do something and make it, bring it to the original documentation. Same idea. Huffman code is one of the ways to measure what things occur, how many times, construct a heap like a tree, and then we use those information to create a smaller code, smaller file. So later, if you take a look at the Huffman tree and your encoded files, the compressed file, you may be able to get back to the original documentations. That was the idea of compression. And the sheet of paper, the extra sheet of paper have one example on it. I will take a look at it with you. It uses extended binary trees. Extended binary tree. Why do they say extended binary trees? We'll take a look. Variable length code that satisfies the property where no code is prefix of another. Huffman tree is a binary tree with the minimum weights, external path lengths for a given set of frequencies, weights. Unfortunately, our textbook doesn't explain that well for the Huffman code. It's a bit messy, in my opinion. So you can certainly take a look at the Huffman code in your textbook. The one I'm giving to you is slightly different looking, but either way is fine. 책에 있는 Huffman 코드가 약간 예제랑 설명이랑 조금 오히려 더 너무 복잡하게 된 것 같아서 제가 그 다음에 주는 거 있지? In in the textbook is 12.63. You can certainly read it. You might find that it's slightly different looking from this example, but either way. So I recommend you to get the idea from this one. It's much simpler than the textbook. 왜 그런지 모르겠는데 약간 Huffman Code 약간 좀 부실한 것 같아서. We show you some examples. Let's take a look at this Huffman tree generation and why is it better, how this tree can be used to compress and decompress the code. Let's take a look. Let's say you have a set of numbers and their frequencies of its use, wanting to create a Huffman encoding for them. Huffman encoding. Encoding here means the same thing as making a compression. Encoding, we're gonna take a sentence, make it into some like 0, 1, 2. So smaller ones. So this is the value. This is the value. This is the frequency. So take a look at it. 1 appears 5 times. 2 appears 7 times. 3, 10 times. 4, 15. That way. Okay. So in order to create a Huffman tree is simple. Sort the list by frequency and make it 2 lowest elements into a leaves and creating a parent node with the frequency that is the sum of the 2 lower elements in the frequencies. 2 sentences explaining stuff is too much, but it's simple as sort this out, sort by the frequencies, get the lowest 2 frequencies. If it's already been sorted, what is the lowest 2 frequencies? 5 and 7. 5 and 7. So I put that as a leaf. Leaf should be the bottom of the tree. It doesn't have any children in it. No. Leaf. 5 and 7. 5. They go right this way. 5 is 1. 5 is 1. 7 is 2 now. 2. It says, make this as a leaf. The parents will be the sum of this frequencies. 5 plus 7, 12. Do this. Okay, that's the first procedure. Continue this procedure for rest of the elements. How? 2 elements are removed from a list, and the new parent node 12 is now ready with the frequency 12, and is inserted into a list by its frequencies. So I'm gonna insert this into the original list. Without 5, 7 is now gone. So what I have is now 10. 10 is the next lowest one. 10, 12 that I inserted into the list again. This is my new parent node. And then 15, 20, 45. I repeat the same process for selecting the lowest one and then making a new parent node. What is the lowest one in the new list? 10 and 12. Yeah, 10 and 12. Just gonna follow the 10 and 12. So I'm gonna 10 and 12 go like 10. 10이 뭐였지? 3? Value 3?
네.
10 plus 22, 22. I don't know what's in. There's no value on this. Frequencies. What's my next step then? Same thing, repeating myself. 22 will be into the new list. 그죠? 22 will be into the new list, whatever left over. And then I do the sorting again, get the minimum of 2. The same in 15 and 20, 22, 45. 15 and 20 is the next lowest one. You do this until there's no elements in it. So, well. 적어본 거예요. 나 잊어버릴까봐. So 15 and 20, 20. 15 is 4. 20 뭐야? 20 뭐니? Value, what is value for 25? 35. Right? Yeah. And now, then I have 22, 35. What was the last one? 45. Probably the last one. Last one. So I select the one, now 22 and 35. So I create this. Let's take a look at this one. 이거 좀 잘리긴 했는데. 22 and 35, you will have a new node for 57. And then this side is 22, 35. 아이고 크다. 뭐 얼마냐? 57. 맞나? 맞지?
네.
Okay. The last one is now I have 45 left, and my 57 is the new biggest one. So I'm gonna merge those two into a one. I'm just follow their ways. 45 is what? 6? 다음 얼마니? 57 plus 45 is what? 불러봐.
120.
머리 좋은 분들이 이렇게 암산을 하면 Done. My Huffman tree. Done. I don't have any other leftovers. This is my final Huffman tree. What is this? Doesn't mean anything yet. Doesn't mean anything yet. Okay, how can I use this to construct a encoding and elements? Encoding and elements. Okay, now the list is just one element containing 1 and 2, the final frequency, and you're done. This elements become the root of your binary Huffman tree. To generate the Huffman code, with this tree you can create something called Huffman code, that is encoding bits. To generate the Huffman code, you traverse the tree to the value that you want it to. So if I wanted to have a value of 2, I do this. Every time I make a left in my tree, I put 0. Every time I make a right in my tree, I put 1. So outputting 0 every time when you take the left decision, and opposite 1 every time you take a right-handed. Normally you traverse the tree backward from the code that you wanted to build the binary Huffman code tree string backward as well, since the first bit must start from the top. Forget about that what's in the parenthesis. Example will be much similar, much clearer. I like to encoding a value for 4. Where's my 4? 4. I like to send 4. I like to send 4. Encoding. 0, 1, 0. 0, 1, 0 is my new 4. So 0, 1, 0 will be 4, the present new 4. Encoding value for 6 is what? Encoding value for 6. 1, because it's stupid. So next time if I want to send 6, this one's 1. You don't see the power of this tree yet. Why do you think it's powerful? Why do you think it can be used as a compression? 왜 그럴까? 아래 example 볼 것도 없이. Notice that this is 57. So lot of times that I'm gonna send 6, which says 45 times in a certain times. The ones that I send many times will be in just 1 bit. The ones that I will send a bit less times than the ones, only 15 times, compared to 45 times, 15 times small. I require larger bits. So if you encode a very long sequence of string, most frequent one just 1 bit, less frequent one will be take more than a few bits. So overall, you can compress the original file into smaller components. 많이 쓰는 거를 계속 6이 그만큼 많이 보내잖아. 45번 보내야 되잖아. 근데 미쳤나 보다. 거꾸로 생각해봐. 6을 45번이나 보냈는데 6을 예를 들어 3비트를 보낸다고 생각해봐. 그만큼 많이 보내야 되겠죠? 비트를 많이 보내야 되겠는데 많이 보내는 걸 작은 비트로 만들어 놓으면 전체를 보내는 게 계속 줄겠죠? 그죠? So you see, that's why they consider the frequency. Larger frequency, smaller bits. Less frequency, relatively less frequency will be larger bits. Same way 0101. So when you have an encoding, you not later you send this encodings only. Encodings only. 4, 6 보낼 때 0101 보내고, and then you also need to share this Huffman tree too. So that's how you recover the original value as well. 트리도 같이 트리도 같이 가지고 있어야 반대쪽에서 트리를 보고 원래 값들을 찾아낼 수가 있겠죠. Example first. The encoding for value 4 is 010. Encoding for value 6 is 1. Decoding a Huffman tree is just as easy. As you read the bits from your input stream, you traverse the tree beginning to the root. So once you have a Huffman encoding, you read the encoding 01 이렇게 보내면 0101 for example. I send 0101 to the other part. How do you bring it back? I just simply follow this way. 0, 1, 0. As soon as I hit the leaf node. Because every leaf has a value. Now you see that every leaf has a value. So as soon as you follow these bits, as soon as you see a leaf node, you print out the value. 1, 1, 6. It's also easy to recover. 거꾸로 만드는 거 보여주고 받았을 때 다시 복구하는 거 보여줬죠. Compression, decompression. Compression, decompression. 뭐 여기 there is a lot of examples that I give you. It's the same ideas. So they say they wanted to send some data that long, only takes 23 bits. So it's a lot of compression. That's what they means to say. Easiest way out with Huffman Code is starting from root dump first, left side, right hand side. For each node, you output 0, 1. By n bits, we print the value. For example, party tree, blah blah blah. 똑같네. 001, 011. 6-bit byte indicates how many bits value for each leaf is stored in case 4. Well, you can read it through. They suggest there's some variation, but this is a key idea, having a Huffman Code tree. 이거는 그냥 참고로 읽어보셔도 되고, 뭐 어떤 예제를 해보니까 좀 줄었더라. 근데 좀 보내는 방법도 좀 다르게 해서 보내는 한 거고, 저거는 뭐 보셔도 되고 안 보셔도 되고. Basic idea for this Huffman tree. Number bits. less frequency, lower bits, less frequency, smaller bits, much more higher frequencies. So you can decompress the bits minimum as possible. So you should know how to construct a Huffman tree from the simple examples. Algorithms. Well, the algorithm is quite easy. Every time you do a sorting, with the minimum 2, construct a new one with their frequencies, and you put that back into the heap, for example. Now you have a 만들고 다시 you need to sort them again with the new values. So in a way, we were using a heap in this one, in those sorting algorithms. So that's it. That's Huffman Code. That's Huffman Code. So those are the very basics for a compression algorithms. And sometimes I ask for implementation for this. 근데 실제로 implementation 하면 그렇게 또 생각보다 쉽지는 않아요. 리스트로 링크 리스트로 만들고 하니까. It's up to you. I think I forgot, but I think in the textbook they provided some part of the code implementing this, making Huffman tree. Huffman code tree. Huffman tree. 뭐라고 그냥? Huffman tree. That might be better. Does it make sense? 말돼? 쉽죠? 그려놓으니까. But like always, I ask you to do one practice. Just follow with your own hands and draw this tree and just do this encoding once. 0, 1, 0, and you maybe you wanted to send a certain string. Just do the practice. You'd like to send 1, 2, 3, 4, 5, 6, whatever. I mean, it has to be long enough so you can see the advantages of the Huffman code, Huffman tree. Close it. So I think we're done on this Huffman tree. 누군지 모르지만 처음에 이거 한 사람들은 머리가 좋은 사람들이죠. 이렇게 보니까 되게 쉬워 보이지. 아무것도 없는 상태에서 이걸 해보라고 했으면 얼마나 머리가 좋겠어요. 컴프레션이라는 전체를 생각을 한 거니까. 최소한의 비트로 최소한 조금 보내면 빨리 보낼 수 있으니까 나중에 받는 쪽에서 또 복구할 수 있게 만들어야 되고. 머리가 좋지. 여러 가지를 많이 구현한 거. 아마 허프만 이름일 거야. 허프만이 만든 사람 이름일 거야. 맞나? 확인 한번 해봐야 돼. 잊어버렸어. So maybe if you can build your own algorithm name after you, Kim Park. I'm sure no one's gonna use it, but we can do it. 알집 만든 분도 알집도 아마 비슷한 아이디어일 거예요. 근데 나 알집은 정확히 알고 있는 거죠. Okay, so we are done in this hip. Take a look at the textbook over the weekend again. We're almost done. I might have to ask your opinions later whether you want to do an extra chapter or not. 나중에 한번 물어보려고 다음 주쯤에 챕터를 하나 뭐 할 건지. 그러면 거의 다 하는 것 같아. 책까지 다 거의 다 하는 것 같거든요. 그렇게 할지. 근데 그게 굳이 알아야 되는 챕터는 아니어서 그걸 하지 말고 그냥 남은 시간은 리뷰 한번 하고 조금 더 다른 거 한 번 더 보든지 그렇게 하는 게 어떨까 싶기도 하고. 책 다 끝내면 배웠잖아. 어차피 거의 다 끝내줬죠. I forgot which chapter this is. Binary search tree. It's all variations of different tree. Now we would like to use this tree, binary tree I'd like to make a better tree. Things are sorted anyways in the first place. So things to consider probably the kind of complexity of sorting a binary tree, finding an element in the tree, But it's a binary tree. If it's any of the searching algorithms, then what might be the possible time complexity of finding an element in binary tree? Doesn't really matter if it's a search tree or not. But binary tree. Yeah. You can now easily guess probably log n is the one they're looking for. And the search, because they put a search tree, they probably guaranteed for finding an elements in log n ways, log n time complexity. Let's take a look. Search tree is ideal for implementing a dictionary. What was a dictionary again? When we keys, right? Keys and values. We store a pair. So if you give in a key, you can find the value right away. So this binary search tree is the best approach to implementing the dictionaries. When we start dictionaries, what was another thing that we also discussed in the same chapter? Hash, right? Hash keys and those type of different data structure we also discussed. Similar or better performance than skip list and hash tables. Skip list. Skip list. The list with the extra pointers in it, you might be able to skip a couple elements in its way, right? To discuss that. So, 어떻게 그랬었어? How do you draw that skip list? 이렇게 리스트 그려. 어우씨, 잘 그렸는데 내가 봐도. 지우기가 안 보여줍니다. Skip list. 이렇게 그렸구나. 그 어레이를 냈었다고. 이렇게 하고. Every 4. Yeah. Likewise, here. Was it? Right? Having extra pointers, skipping the other ones. They wanted to get there fast, skipping. If you're sure that the elements that you're looking for in this way not there, I just skip to the second one. And I think they also put it as some type of levels. So let's say if we use a search tree, right, then we might have a similar performance to a skip list and hash table. Good, good. Particularly ideal for accessing sequential or by the rank. Rank is 등수 1, 2, 3, 4, 5, 6. If you want to put a rank, it's probably they also discussing for these sortings, ascending, descending order, which one is the biggest, smallest. In this chapter, I forgot the chapter number. This is chapter 12 or what? 14? Okay. Sorry. 미안해. 13을 우리가 스킵했나? 네. 그죠? 14, this chapter we will learn binary search tree, indexed binary search tree. Indexed. Same thing, maybe has the same meaning as putting a number for each node. And let's take a look at what's a binary tree. Binary search tree. We know what's a binary tree right now. Binary search tree definition. A binary tree that may be empty. A non-empty binary search tree satisfies the following properties. A non-empty binary search tree satisfies the following conditions, and you can call that as a binary tree. 1. Each node has a key or value, and no two nodes have the same key. Good. All the keys are distinct. Second, for every node X, all elements in the left subtree of an X smaller than it's in X. So I'm in the root. This is me. I have a child on my left side and right side. It says everything on my left side will be smaller than me. Smaller than. Likewise, everything on the right side of the tree will be bigger than me. Value will be bigger than me. clear. It's clear. 여기는 나보다 작고 여기는 나보다 크고. It's guaranteed for the binary search properties. The left and right subtree of the root also binary search tree. Left side of my tree is also binary search tree. Right side of my tree is also binary search tree. So it means if you go into the left side of the binary search tree, also the root of that left side of subtree will be, the left side will be smaller, right side will be larger. So it's kind of like you're mixing up the min and max tree. Left side is min, right side is max. 그렇죠? 합쳐놓은 것 같은 느낌. Examples, binary tree. Which of the above trees are binary search trees? Take a look at why A is in a binary tree, binary search tree. Top is 20, left one is 15, right one is 25. And then you go into the right subtree, 25, 22. 22 is smaller than 25, but it's on the right side. It violates the third property of a binary search tree. Right side always has to be bigger than its parent. This one, 35 is smaller than 30, okay. 2 is smaller than 5, okay. 40 is bigger than 30, so that satisfy the binary search properties. C, 60, there's nothing on my left side. Yeah. Right side is 70, left side is also 65, right side is 80. So every element on this side is bigger than 60. Yeah. It satisfies the conditions for the binary search tree. So B and C is a binary search tree. Y is an A, is a binary search tree, like I say. 22 comes to the right side of 25. It's by the definition of the subtree of the binary search tree, subtree of the binary search tree, also a binary search tree. So that violates the rule. So B and C is the only one there. I forgot my attendances. Shoot. 야, 이게 이렇게 많이 나오는데. I have to put my attendance sheets. Someone, 종이 한 장 줘봐. 자, 종이 한 장 어떻게 주세요? 종이 한 장 뜯어서 사건이랑 이것저것 쭉 돌려서 주세요. 이런 실수를 하다 해버렸어. Maybe let's take a look at this page and I will let you go. 그럼 가기 전에 이거 꼭 적어요. 치우고 적어주지 마요. Index binary search tree. Definition: binary search tree is a binary search tree. Each node has an addition left field left side. Support the search and delete operation by rank as well as the binary search tree operation. Left side. What is the left side? Left side. The number of elements on its left subtree. And then I put that number beside the node. There. The rank of the element with respect to the element in the subtree. Force elements in the sorted order. We'll take a look at the example in next class and I'll let you go today. Make sure you write those attendance sheets and
나중에 갖다 줄래요? 아니면 나중에 데이터베이스 시간.
오케이? 추석을 안 보러 끝내니까 되게 허전합니다. 뭘 안 하는 것 같은데. 여기다 꼭 적어서 주세요. Okay. Any questions for today? Any questions? Okay. 수고하셨습니다.
고맙습니다.
네.